talks and a panel discussion, and in these three talks there'll be a flavor of science with TMT, technology and industry partnership. So first speaker is Dr. Ravinder Bhatia, Associate Project Director of TMT Project from TMT US office. Yeah.
Thank you. Pleasure for me to be here this evening. I'm going to talk about the 30-meter telescope, and this talk is an overview of the observatory, and Professor Ram Prakash will follow with a talk which is more focused on the contributions from within India itself to TMT. So in this talk, the objectives are really to give a flavor, a sense of the different types of science that we'll be doing with TMT. I'll provide a status report on the project, and I'll talk a little bit about the international partnership that is creating and will be operating the 30-meter telescope. So science goals. The TMT really is a workhorse. It's an observatory that is focused on performing a wide variety of scientific research. And these range from fundamental physics and cosmology all the way through to the early universe, looking at black holes and galaxies, star formation, exoplanets, time domain science, and also, of course, the solar system. And it was interesting looking at the poster that is surrounding us and the different science themes here, and recognizing just how much of those topics TMT will cover. Not just itself, of course, but in collaboration with a number of other observatories as part of this move within astronomy towards multi-messenger astronomy, and both the other ground-based and space-based observatories that are either already existing or in the planning stage for deployment soon. So on this chart, again, we're looking at the discovery space for TMT, and the axes here. So this is spatial resolution, and we are also plotting here spectral resolution. And on this, let's take exoplanets, for example. I'm going to be talking about exoplanets as one example science theme for TMT. Here we have the mix of the flux from the star and an exoplanet orbiting around that star. And at the different wavelengths, we can look at the individual constituents of the atmosphere of the exoplanet, and at the very highest resolutions to be able to, and what I mean by that is the smallest space that we actually look at, we can see through direct imaging the exoplanet itself. And to talk a little more about the exoplanets, this is a plot, it's an image, a movie showing the different detections of exoplanets that have taken place over the past 3 decades. And there are many different ways of looking at and detecting exoplanets. I'm not going to describe them all here for the sake of time, but these observations have been primarily made over the past 2 decades, and a particular area of interest with the 30-meter telescope now, with the very large mirror that we have and the sensitivity that we have of the scientific instruments, is to look at direct detection and through direct imaging. For this, we'll be using an adaptive optics system to really eliminate as much as possible the effects of Earth's atmosphere. And then we'll be using coronagraph to mask out the flux from the star so that we're left with the flux from the exoplanet itself. And these are some observations that have been made over the past few years from another ground-based facility, which gives you just, again, a flavor of the kinds of science that we'll be doing in the future with TMT. Of course, one of the overarching motivating factors now for exoplanet research is this question of whether there is life on other planets out there. And with the different biosignatures that we can see here with the different chemical species, a number of these are accessible in the windows that TMT will observe at from the ground, from the top of a mountain, of course, so that we'll be able to pick up the different spectral signatures and identify what those chemical constituents are in the atmospheres of those exoplanets. Another example of a theme, black holes. Of course, we have the overlapping areas of research with LIGO that was discussed earlier today, and with TMT and the capabilities, for example, from the Indian contribution to LIGO to be able to zoom in and understand better where these gravitational waves are coming from. We can use TMT as one of the observatories looking at the electromagnetic radiation for follow-up observations. And here some of the core themes are when did the first of the supermassive black holes actually form? What are those black hole properties? How do those black holes evolve as the galaxies within which the black holes are embedded evolve? What are those relationships? What are the feedback mechanisms as those objects grow with time? Those dynamics of black hole evolution as well. So this is an example of observations made with the Keck Observatory. And here, so we're plotting with high precision the orbits of these stars. For the stars that are orbiting close by, they orbit very, very quickly. And close by, we can basically map out where we think these black holes are. So this is a technique that has been used in our own Milky Way, and we'll be extending this to other nearby galaxies with TMT, the same approach, to look at other supermassive black holes in other nearby galaxies. And there are other techniques, again, I won't go into them here, reverberation mapping and so forth, that can be used for understanding the characteristics of black holes that TMT will be contributing to. Here is an example of a visual example of the improvements in seeing that we will get with the 30-meter telescope. On the left, you can see a wonderful image from a wonderful observatory, the Hubble Space Telescope. So looking at this globular cluster, if you were to zoom into the center, you'd get this kind of pixelization effect given the capabilities of Hubble and its instruments suite. Just for comparison, and this is a model, but in comparison, this is what TMT will be able to see with one of its first generation instruments compared to the Hubble Space Telescope. So it's true, it's a very simplistic comparison, but nonetheless, I do think it's illustrative and very easily seen in terms of the improvements that we'll get with the 30-meter telescope compared to even a space-based observatory such as Hubble. Let me talk now about the observatory itself. So here, this is just the light path. The light reflects off a primary mirror, the 30-meter mirror here. The secondary mirror is up here. The light bounces back down to a tertiary mirror, which is a flat mirror, and the light goes off to the science instruments on either side. This is a fly-through of the observatory itself. So going up and then down past the enclosure, you can see the primary mirror. Looking past the secondary there, you can see the flat tertiary and the instrument suites on the side. And we have this very elegant shaped calotte enclosure to protect the delicate instruments and mirrors inside. This is an image of the 30-meter mirror itself. And because this is 30 meters wide, we actually make this mirror out of hundreds of small segments, each of them about 1.5 meters across. They're segments that we put side by side. And each piece of glass is actually fabricated, melted in Japan at our industrial partners there, managed by the National Astronomical Observatories of Japan. And these are, there are actually hundreds, half of these, the total quantity of these blanks have already been fabricated. Many of them have been sent to the US. Some of them are being sent soon to China, and we're in planning for sending the first of these also to Bangalore. India has one of the polishing facilities. We have these hundreds of segments that will be polished in one of 4 places, in India, in Japan, in China, and also the United States. So each of these places will polish roughly 100, 150 of these pieces, depending on how much in-kind contribution that particular country is making. The glass, once it's finished, is machined into a hex. There are pockets that are ground in to take the edge sensors and the control system that India is fabricating. We do iron beam figuring to the final polished surface to get the final high precision surface that we need. Then we're mounting these on segment supports that are, again, all of these, several hundred of these will be fabricated here in India's high precision mechanical contributions. The primary mirror control system also has actuators and edge sensors that are all being fabricated. There are thousands of these being fabricated here in India. The secondary mirror is work that's still to be in progress. The tertiary mirror is being done in China. They've done a quarter-scale prototype and moving forward rapidly with the final design of this, going into the final design phase soon. We have an adaptive optics system that I mentioned earlier. The way the adaptive optics system works is to basically compensate for the turbulence introduced by the Earth's atmosphere. And we can get, as you can see here in comparison, much higher precision pointing through the adaptive optics systems. Here, Saturn without adaptive optics, Saturn with adaptive optics. The way that this works is that if we have, for example, our science target being a galaxy, we look at a star close by that we know what that looks like. It's a bright star that we choose. The light comes down through our atmosphere to a detector, and it's passing through Earth's turbulence here. Now, if we can put in place a deformable mirror and essentially operate that deformable mirror in antiphase to take out the turbulence, then we end up with a kind of straight wavefronts coming onto our final detector system. So on TMT, this is a fairly complex system. It looks like this. We have lasers to help us as an alternative to what we call natural guide stars. We can shoot up lasers into the sky to be close to our science target. These are transferred up the beam transfer optics to the back of the secondary mirror and then launched from here up into the sky. And the return light from our science object is focused, as I had described, via the tertiary mirror onto the science instruments on the side. In this particular case, Nefarious is our adaptive optics facility being designed and built in Canada. And this is one of the science instruments underneath to do the imaging and spectroscopy. IRIS will operate over a wavelength range of just under 1 micron out to 2.5 microns. So essentially it encompasses the optical and infrared ranges, which give us a very broad range of science topics that we can do. And because IRIS benefits from this adaptive optics system, we also have very high spatial resolution that we'll be able to take advantage of. Another first light instrument is WFOS is our wide field optical spectrograph, and this doesn't take advantage of the adaptive optics system, but nonetheless has a very, as you can tell from its name, very wide field, which allows us to conduct follow-up surveys very quickly and cover very large patches of the sky. So these instruments are on these platforms off to the side. The call for ideas for second generation instruments has also gone out, and you can see here again I'm plotting wavelength here against spectral resolution. There's a broad range of instruments, and you see some of them repeated because they operate in different modes, but there's been very strong interest from the astronomical community here in India to contribute not just to those first generation instruments but also to contribute and indeed take the leadership on some of the second generation instruments as well. So from the project office, we've been delighted to see this level of interest from India. The telescope structure, which houses all of this and enables the high precision pointing, is being developed by Japan. There are thousands of tons of glass and metal that need to be pointed very precisely. So Japan is building the structure. This is also we want to be able to clean the segments every couple of years, so they developed this very nice robot system. Here it's coming down and pulling out one of the segments, which is then taken away for cleaning and recoating if needed. And then here it's bringing in a replacement segment and drops it in. We need to be careful we don't damage the rest of the mirror segments as this is going on. So we have to be very careful with respect to safety and high precision. And it was really nice to see the prototype of this when I was in Osaka on one of my trips there. And it was really an impressive piece of work. The enclosure, again, I mentioned it was a calotte system. It's being designed by our colleagues in Canada, and this is the fabrication sequence. You see the false work here, and it encompasses this really elegant design that I always am impressed with, the way that this is being put together. As well as the hardware, there's an awful lot of software that's being developed, and India is taking the lead on all of the software that is being developed for the observatory. The site status we want to build in Hawaii. There have been problems in the past with the protesters there. We have full legal clearance, and we hope to go to our baseline site perhaps later this year. And in the meantime, we're engaging very closely with the communities in Hawaii. We do a lot of work in terms of education and workforce development and supporting community foundations. We do have a backup site, which are the Canary Islands, just off the coast of Africa, Spanish territory. These are the countries I've been mentioning, and India is contributing of the order of about $150 million worth. All of the countries contribute a mix of, certainly dollars in terms of cash contributions, and certainly hardware. Some of the countries, primarily India, as I said, is taking the lead on software. So not all of the countries are doing much software. In exchange for all of this, the observing time that the country gets is proportional to the investment that's been put in. This is a photo that was taken when India joined TMT. I think this was 2013? 14, thank you. Just to wrap up, I was interested to see, what fraction of the world's population is actually represented here by the partnership of TMT. So this is over the construction phase. These are UN figures in terms of population. So it's about 3.5 billion people here out of 5. There's a rapid increase in population, projected at least. And so I was interested over the operational lifetime of TMT. This was news to me. It would kind of stabilize roughly 3.5–4 billion, which is still a sizable fraction of the world's population represented here. And of course, with all of the different cultures, it's not just a technological challenge or a scientific challenge to build TMT, but to have all of those different cultures working together as one team has its own challenges, as I'm sure you know. So to summarize and to conclude this talk, we will be undertaking, I think, compelling astronomy in many different fields. We've benefited enormously from the international collaboration, with India taking not just a supporting role, but a leading role in developing the technologies and providing the scientific expertise. We hope to restart construction on Mauna Kea later this year to start our first observations a decade from now. Thank you.